Okay, so hi there, everybody. In this next video on number theory, we're going to talk about the divisibility theory still. In our past, past videos, we have talked about this module, divisibility theory and the fundamental theorem of arithmetic. So in the last video, we have asked a question that, how many primes are there? So in this video, we're going to present the answer for that. And let's give this a straightforward answer for now. So the answer here actually is attributed from Euclid, Euclid himself, the author of the Elements, the famous Elements. So Euclid said that the answer for this, that there are infinitely, infi, that should be an I, infinitely many primes. Okay, so there are infinitely many primes, so meaning you can say that the primes are infinite because that's what Euclid said. But of course, Euclid have a proof for this, in which we are going to show also in this video. Okay, so before we can even answer this question, or before we can even show the Euclid's proof for this, we shall need the following lemma. So remember, a lemma is a minor result to prove a major theorem. Okay, so we shall prove this by induction, specifically by strong induction. Okay, so let's have it. So what does the lemma says or say? Oops. Okay, there you go. Okay, so this lemma says that, okay, so every integer greater than or equal to 2 has a prime factor. Oops, prime factor. So all the integers greater than or equal to 2 has a prime factor. So meaning it has a factor which is a prime. Okay, so we're going to give this a proof. This proof will be via strong induction. So let's give a proof over this. We are using by strong induction. To remember the strong induction, the second principle of mathematical induction is also known as a strong induction. So if you want to prove some that this statement is going to be true for all natural numbers, so what you're going to do to prove the k plus 1, you need to prove n sub 0 up until k, and then that will eventually give us the proof that k plus 1 is true if you have proved all the cases from n sub 0 to k. Okay, so by strong induction, so what we're going to do clearly for the first part, so clearly it is true when n equals 2. So when n equals 2, so imagine if your n is 2, if your integer is 2, so it has a prime factor which is 2. Okay, so n equals 2, it is clearly true. Okay, now for the second case, now it is true for every positive integer. Now let's assume, okay, now assume, let's try to fit that. Now assume it is true for every positive integer n, which is less than or equal to k, where k is greater than or equal to 2. Okay, so we have this assume that all it is true for all integers n, which is less than or equal to k, where k is greater than or equal to 2. Now we will consider the integer. Consider the integer k plus 1. Oops, let's write that properly. K plus 1. Okay, so we'll have two cases for this, and let's prove them one by one. Let's show them one by one. Okay, let's try to pick a bit. So for case one, case one. Okay, shall we have this? First case will be, okay, if k plus one is a prime. So if it is a prime, then it is a prime factor of itself, surely, right? Because it's a prime, for example, 17. So it has a prime factor of 17 because its prime factor is itself. Then k plus 1 is a prime factor of itself. Factor of itself. Okay. So how about for case number two? Case number two will supplement the or complement the case number one. So again, case one is for k plus 1 is prime. For case two, let's say, how about if it is not prime? Say if it is composite. So if k plus 1 is not prime, is non-prime, it's not a prime. Let's make that to make it simpler in language. So if k plus 1 is not a prime, so it must be composite, right? So it must be composite. So if it is composite, uh, so it must have a factor. It must have a factor since it's composite. Since it's composite, so it must have a factor d, that we say that d is greater than or less than or equal to k. Of course, its factor should be less than itself or equal to itself. It can be. Okay. So then we say then by the induction hypothesis, by the induction hypothesis, induction hypothesis, d. So this d here, this factor has a prime factor of p. Okay, because this d, if it is not prime, or it has a prime factor of p. D has a prime factor p. So by theorem one, if you can remember theorem one, or rather theorem two. So we have a video on theorem two about transitivity. So if A is a factor of B and B is a factor of C, so therefore A is a factor of C. So we can see here that P is a prime factor of D, and also D is a factor of k plus 1. So again, if P, rather, let's make use of the word factor instead of prime factor. If P is a factor of D, so therefore we say that in symbols, um, P is a factor of D, and also we know that D is a factor of k plus 1. Oops, where can I write this? Let's write it here. Let's just erase it afterwards. Okay, so if P is a factor of D and D is a factor of k plus 1. So by theorem number 2, that is transitivity, P is a factor of k plus 1. Okay? So that's transitivity. Okay? So by theorem 1, we say then that, um, you know, let's move this a bit. There's no more space, but let's make that fit. By theorem 1, or 2 rather, in our book, by theorem 2, P is a factor of k plus 1. Okay, so thus by the strong version of induction, the statement is true for every integer greater than or equal to 2. So there's no space down below. Let's put it here. Beside it, there's just proof there. So let's put it here. Um, okay, So, oops. So by the strong version of induction, so hence, oops, hence by the strong version of induction, the statement is true for every integer. The statement is true for every integer greater than or equal to 2. So that is every integer greater than or equal to 2 has a prime factor. And the theorem holds. Okay, so that's our proof for this theorem. So we're just saying that it is true that for every integer greater than or equal to 2, it has a prime factor of itself. Or rather, it has a sub prime factor. Okay, it can be itself. Okay, so there it is. So every integer greater than or equal to 2 has a prime factor. Okay, so let's continue with this theorem. Again, we want to answer the question, how many primes are there? So we're going to make use of this lemma, okay, in this theorem. So let's have it. Let's put some space here. Oops. Okay. I think that's it. Okay. So let's write this in formal setting. So let's say theorem, and we will call this Euclid's theorem. Theorem. So this is Euclid's theorem. This is by Euclid. Okay, Euclid. And what does this theorem say? It simply says that there are infinitely, oops, there are infinitely many primes. Okay, many primes. Okay, so let's give a proof for this. Again, we're going to make use of that lemma before. So we're going to prove this by contradiction. Okay, so let's assume since there are infinitely many primes, so we can I think it's very clear that we cannot we cannot give direct proof for this, because we cannot simply say that there are infinitely many primes, because a direct proof will be a bit, not that trustworthy. So for example, you just say that there are infinitely many primes, but you cannot prove that there are the infinite number. So you cannot prove the infinite number of primes. So let's just do this, or prove this by a contradiction. That is, we're going to assume that there are finitely many primes. That's the false statement. And then we're going to say that that false statement cannot be true. So indirectly saying that the original statement is false. Again, so that is by contradiction. Let's make this true statement, false, meaning we have a falsified statement, and we will be falsifying that falsified statement, indirectly saying that the original statement is true. Okay, so that's the essence of contradiction. So again, let's assume that this is false, meaning if there are infinitely many primes, we will assume that there are finitely many primes. So assume there is only a finite, there is only a finite number of primes primes, and we're going to name that primes since they are finite. So we're going to name them p sub 1, p sub 2, p sub 3, up until p sub n. Okay, since they are finite, so we stop at this certain n, okay, until, meaning that's the last prime. That's the highest prime, okay, along the number of primes, because they are only finite. They are finite, so meaning they can be counted. So consider the integer n. We will consider such integer, this integer n, where n is equal to, okay, n is equal to the product of p sub 1, the first prime, p sub 2, the second prime, p sub 3, the third prime, and so on. Let's put that as a center dot, meaning multiplication, until p sub n, the last prime, and then we're going to multiply all the primes themselves, and then after multiplying all the primes, we're going to add 1. Okay, so now we say since n is greater than or equal to 2, that is very clear because the first prime is 2, the second prime is 3, the third prime is 5. So if we're going to multiply all the primes up until the last prime, it is surely greater than or equal to 2. Okay, so by using the lemma, by the previous lemma, let's move the, oops. Okay, so by the previous lemma, by the previous presented lemma, that's a lot of space. Let's save space. Okay. Um, n is divisible by some prime p sub n. So n is divisible by some prime we will call p sub I. Okay, so yeah, so n is divisible by some prime p sub I, where I is strictly, not really strictly, less than or equal to n, or it can be greater than or equal to 1. So it can be the first prime, it can be the last prime, but I could be anywhere along the number of primes. Okay, along these primes here. Now we say since p sub I is a factor of n, or divides n, and also p sub I is a factor of p sub 1 times p sub 2. Oh, sorry, I have some mistakes here. This shouldn't be a comma. Sorry, they must be multiplied, so there shouldn't be any commas there. Instead, it should be raised dots. But even though without raised dots, variables put together are understood to be multiplication. The operation there must be multiplication, so it can be written like that. So not as commas. Okay, my bad. So let's put here raised dots so that it will be clear. P sub 1 times p sub 2 times p sub 3 multiplied continuously until the p sub n. So p sub I is a factor of p sub 1, p sub 2, p sub 3 up until p sub n. And we also lastly say that p sub I is also a factor of n minus p sub 1 times p sub 2 times p sub 3 up until p sub n. So if this is the case, we can say by theorem 2 or by the transitivity theorem that we have proved in the last video. So by theorem 2, by theorem 2, since p sub I is a factor of n, and p sub I is a factor of p sub 1, p sub 2, p sub 3, p sub n. Okay, so we have therefore p sub I is a factor of p sub n minus p sub 1, p sub 2, p sub 3, up until p sub n. So by theorem 2, that's by theorem 2. So that is, we simply say that p sub I is a factor of 1, okay, which is impossible. Okay, how did we get the 1? So since n minus all of this, okay, n minus all of this, okay, will give us 1 because, transposing this factor to the other side will give us the value 1 on the this side. So we have n minus p sub 1, p sub 2, p sub 3, up p sub n will be equal to 1. So we have applied the theorem to over here actually. So since p of n is a factor of n, since p of I is a factor of n, and p of I is a factor of all of this, so we can say that p of p sub I is a factor of n minus p sub 1, p sub 2, p sub 3, up until p sub n. So that is by theorem 2. Okay, if you can remember clearly the theorem. Okay, so again, if p sub I is divisible by n, okay, this big number, this we assumed number, And p sub I is also divisible by all the factors, all the primes, the primes, the product of all the primes. So therefore, this p sub I is also a factor of this number minus by this product of primes. So remember, the value of this n minus the product of primes by this equation is equal to 1. So we're simply saying that that is by theorem 2. So we infer this statement. So that is, this value is equal to 1. So p sub I is said to be divisible by 1, which is of course impossible. Okay, because p sub I is some prime. And then it turns out that it's divisible by 1. So therefore, that is impossible. So this is a contradiction, shall we say. Thus we say our assumption is false. So therefore, we have a false assumption that there are finitely many primes, telling us, okay, so telling us indirectly that there are infinitely many primes. And then that's the end of proof. Okay, so that's it for this video. I hope you got it. And then, yeah, I hope you will like and subscribe. So thank you very much for watching, and I'll be seeing you soon. Okay, goodbye.